Okay guys, so in this video we are going to talk about phenol, a derivative of benzene, a very important compound with respect to the A2 syllabus, and there have been many questions on this in the past papers. So now let's get started. A very important topic. Please take this one very seriously. Okay, first let's do a bit of the naming of phenol compounds. Okay, now the naming is basically quite simple. If we have four different groups, these four groups are halogens, methyl, ethyl, propyl, butyl, any of the alkyl groups. We have the nitro groups, nitro basically the NO2 group, or if we have the amines groups, amines or amines, however you want to pronounce it, amines NH2 group attached to the phenol, then we are going to name that compound as a phenol with all of these as the substituents. These are the substituents on that ring. Now let's see how are we going to name them. For example, I have chlorine attached to a phenol. Okay, this is our phenol, OH, and chlorine atom is at the second carbon. The name becomes, this is the first carbon and this is the second carbon. The name becomes 2-chloro and phenol, 2-chlorophenol. And then if it were a bromine atom over here, then it would have become bromophenol, 2-bromophenol, 2-iodophenol, and so on. Okay, if there were two chlorine atoms attached to the phenol, then it would have become, and the second chlorine atom is at the fourth position. So the name then becomes, in that case, becomes 2, 4 dash 2 chlorine atoms, excuse me, 2 chlorine atoms, so dichloro and then phenol. Okay, so this is how we name the phenols containing halogens as the substituents. Then we are gonna talk about the alkyl groups. So basically the methyl group over here, if we have, rather than the chlorine atom, if we have an alkyl group, for example a methyl group attached to, let's say, the fourth position, a methyl group is over here, so then the name just simply becomes 4-methyl and phenol. Simple. And then let's talk about the nitro group. If there is a nitro group, then the name becomes nitrophenol, NO2, 4-nitro, phenol in that case, 4-nitrophenol. Okay, and what if we have the amine groups? So in the case of amines, the story changes a bit. If we have an NH2 group attached, it becomes 4-. The amine group is called the amino group. You must have heard about amino acids, the amine group, it becomes the amino group, so 4-amino and then phenol. This is how we name phenol derivatives. So this is all that you need to know about the naming in phenol. Now let's get going to the structure of the phenol, which is basically the major part, and the upcoming reactions are going to be based on that structure of phenol. Okay, let's draw the benzene ring over here. This is our benzene ring. Okay, and an O and an H group attached. The oxygen has two lone pairs, so these are the lone pairs of electrons. And as we know that the benzene ring over here has a delocalized pi system, so the orbitals basically, I am ignoring the ring inside. Okay, I'm ignoring the ring inside and I'm making the individual orbitals. Okay, now these orbitals, as we know, they overlap with each other forming a delocalized pi system. Now the lone pairs of oxygen, they also, since they are directly attached to the benzene ring, they'll also overlap with the delocalized pi system of benzene, forming an extended delocalized pi orbital. And we know, we've even talked about this in the previous video on chlorobenzene, extended delocalized pi system exists. This is a keyword and is used in almost all the answers when explaining phenol. Okay, so remember this word, extended delocalized pi system. This is a key point. Okay, extended delocalized pi system is formed, and how is it formed? The lone pair of oxygen gets delocalized over the benzene ring. Lone pair of oxygen is delocalized or distributed over the benzene ring, over the benzene ring. Okay, so this is basically the structure of phenol. Okay, now this extended delocalized pi system, it gives the phenol a characteristic property. That characteristic property is that this carbon oxygen bond over here, the carbon dash oxygen bond over here, it gets a partial double bond character. It gets a partial double bond character. Why does it get a partial double bond character and why not a full double bond character? That's because this is not a permanent double bond. It's basically a bond which is formed by the delocalization of the lone pair over the benzene ring. Okay, so carbon oxygen bond that's why the carbon oxygen bond gets a partial double bond character. Now, the partial double bond character means that this bond becomes very strong and it is difficult to break. The bond becomes stronger. Basically, this bond is stronger than a carbon oxygen single bond and it is difficult to break it. Difficult to break. If we compare the bond length of carbon oxygen bonds, carbon oxygen single bond, carbon oxygen bond in phenol, and carbon oxygen double bond. The bond lengths in nanometer. Carbon oxygen single bond, for example, in alcohols, has a bond length of 0.143 nanometer approximately. Carbon oxygen double bond has a bond length of 0.1 to 2 nanometers. As we know that as the bond becomes stronger, the bond length decreases. This is a general trend. The carbon oxygen bond is stronger than the carbon oxygen single bond, but this carbon oxygen bond in phenol is weaker than the carbon oxygen double bond. So it has a bond length which is intermediate in between the two bond lengths and it's 0.136 nanometer. Okay, so this is an important point. Uh, it gets a partial double bond character due to the extended delocalized pi orbital, which is formed due to the overlap of lone pairs of oxygen. Thank you so much. See you in the next video.